Here's a vertical curve example with a control point. This is kind of a classic vertical curve example where you don't know the length in advance, but you have some information about a control point along the alignment, and then you use the quadratic formula to calculate the length. So we're given some information. It's always an equal tangent vertical curve. The initial grade is -2%, the final grade is +1%. We have the station and elevation of the PVI, station 110, and elevation 420 feet. There's a street crossing perpendicular to this roadway at station 112, and the crossing elevation must be 424.5 feet. So the challenge here, as it states, is to design the curve, which basically means to determine the length, and then to identify the station and elevation of the PVC and the PVT. So as usual, the first thing that we'll do is draw the picture. Okay, now we've drawn the picture, and as you can see, I've illustrated here the unknown total length of the curve. We're going to use the fact that this is L over 2, so I've labeled that. We also know the distance from the PVI to the road crossing at station 112 is 200 feet, so I've labeled that just to make it a little bit easier. And we're going to use this offset distance y by extending this 2% tangent forward. So since we know this elevation and we know this elevation, the next thing I want to do is calculate the elevation on the tangent at station 112. So we know the slope, so it's the elevation at 112 is 420 feet minus 200 feet times 2%, 0.02. So this turns out to be 416 feet. So this is 416. So now conveniently, we can calculate the value of y. That's just the elevation of the road crossing, 424.5 minus 416. So that should be 8.5 feet. So label that. So this is going to be the information that we're going to use to solve for L. So we know that the vertical offset for this particular station, for this particular curve, is equal to 8.5 feet. But you also remember that there is an equation for that, and that is ax squared over 200L. So L is the unknown here, and x is just the distance from the PVC to this road crossing. So we can do some substitution. 8.5 equals a times L over 2 plus 200 squared divided by 200L. So of course A we can calculate, as always, is the absolute value of G2 minus G1. So that's the absolute value of plus 1 minus 2. So A in our case is 3. So we can rewrite this 3 times L over 2 plus 200 squared divided by 200L. So fortunately, we have one equation with one unknown, but we have an L squared in there, so we're going to use the quadratic formula to solve for L. So I'm going to simplify this. 8.5 equals 3 times L squared over 4 plus 200L plus 40,000. That's 200 squared divided by 200L. So I can cross multiply, and we have 1700L equals 3L squared over 4 plus 600L plus 120,000. There you go. Whoops. We have 0.75L squared minus 1100 L. If we subtract 1,700 from both sides, plus 120,000 equals 0. Then we can divide everything just to make it nice and clean by 0.75. We have L squared minus 1467L plus 160,000 equals 0. So you can use your calculator, or I think math.com has a quadratic calculator, and you can find that L is either equal to 118 or 1348. We could also solve the quadratic equation manually, and I would recommend that you kind of prove to yourself that you can do that. So in our case, we have two options. So will the value of L equal to 118 work? As you can see here, 118 is less than this distance from the PVI to the control point, so it won't work, so we will discard that one. And we're almost done. We've designed the curve essentially to be 1,348 feet. If I was a designer and I was going to do this, I probably would just say 1,350. But what we want to do now, just to wrap things up, is to calculate station and elevation of the PVC and the PVT. So we can start at the PVI. So we can say that the PVT is, slide this up a bit, is equal to 420 plus 1348 over 2 times 0.01, and that should be 426.7. So the elevation here is 426.7, and the station is 110 plus 1348 over 2, which is 116 plus 74. And then we just do the same thing, but going backwards. The PVC equals 420 plus 1348 over 2 times 2%, and that equals 433.48. And so I'll label this 433.48. And the station there is 103 plus 26. So there we have it, vertical curve designed with a roadway constraint. Classic problem.